today's lesson we're going to be still looking at limits, but we're going to be talking about limits involving infinity. So let's start with this one right here. Now, it does not say anything about grabbing a graphing calculator. Let me hit a little focus here. So we would like to evaluate these limits without technology. Okay. So the first one says, what is the limit as x approaches 3 from the right? And we've got this function right here. Now, when they start asking about from the right or from the left, that typically means that there is something kind of funky going on in the graph, or it's not something that we'll be able to factor, reduce, plug in. So I want to talk about two options for this one. Again, I'm not just going to plug in the 3 because they're not saying at 3, they're saying 3 from the right. And by the way, if I try plugging in the 3, I already get 0 in the bottom, so there's our problem. So one option is to use a graph. Let's graph this function. And by the way, when I look at this parent graph, I see a 1 over x. Now I see that that x is negative. Here's what I'm going to do. I'm going to come, I'm actually going to come over here. I'm going to take that negative to the top. Right, so if it was 3 minus x and I take out a negative, it's now x minus 3. So I like that negative in the top. So now I see the parent graph of 1 over x. It's been moved to the right 3. Right, we remember what 1 over x looks like. Move it to the right 3. We're going to move it up 2. Now that negative is going to flip our graph over, so we're going to be in quadrants 2 and 4. So very quickly we get a very good graph of this function right here. And now it's easy, as we learned the other day, to look at a graph and evaluate the limit. As x approaches 3 from the right, so I'm on the, here's 3. I start on the right side of 3 and I start walking back in. Where is my pen going? It's going down to negative infinity. Okay? So our answer was infinity the other day, but we were just looking at the picture. So if we're given an equation and you know how to draw the picture, well, let's draw it. So your other option, if you don't want to use the graph or you don't know what the graph looks like, is to make your own table. Make our own t-chart with x and y. Now, our goal is to get really close to 3. But we've already said, you know, when you plug in a 3, we're going to have a problem. So just like we did with our pen, we said, well, let's start on the right side and start walking back towards 3. Now, I started with my pen at like 6. I'm going to start, and you're going to think I'm pretty crazy. Notice I left some space in there. You're going 3.1. That's not very far away from 3. I get it, but think about what we were doing with the calculator the other day. We were making that table and we were creeping closer and closer and closer. You'll see why I picked this in just a moment, but I'm going to get even closer than 3.1. How about I do 3.01? Or I could do 3.001. And I could keep, I didn't give myself a lot of space, but I could keep inching my way closer and closer and closer to 3. Let's see why we did that. Let's start down here. If I plug in a 3.1, I get 3 minus 3.1, which is negative 0.1. And I still have a plus 2. Now why do I like that 0.1? Because it's 1/10. And 1 divided by 1/10 is 10. Negative 10 plus 2 is negative 8. So it's not very descriptive, but that's okay. We don't see a pattern because all we have right now is one number. So let's go plug in the 3.01. 3 minus 3.01 is negative 0.01. 0.01 is 1/100th. So 1 divided by 1 over 100 is 100. So negative 100 plus 2 is negative 98. Well, now we're getting somewhere. We could do the same thing. If we haven't seen what's happening to our y values, our y value just jumped from negative 8 to negative 98. Yeah, we're starting to kind of get that idea. It's getting pretty big in the negative direction. Well, if I plug this one in, I get 1 divided by negative 0.001 plus 2. So this is 1/1000th, so I have negative 1,000 plus 2, or negative 998. So look at that pattern. Look at what's happening to the y values. Closer, as I inch closer, to negative, or I'm sorry, to x equals 3, my y values are getting large in the negative direction. So, you know, I honestly think this took us much less time to graph it, but if you don't know what the graph looks like, start plugging in some numbers. Okay, good. Let's take a look at this next one. It's the same function. I'm asking about the limit as x approaches 0 from the left and as x approaches 0 from the right. Ignore this box down here at the bottom. So, well, this is not a parent graph for us. This is not like, hey, let's go graph 1 over x. And honestly, a t-chart doesn't look like a great option because who knows the sign of 0.1 or the sign of 0.001. I think at this point a t-chart is a little overwhelming. So here's what I'm going to do. I'm going to go plug in that 0 if I can. Just kind of hang out with me for a second. E to the 0, that works. E to the 0 is 1. So in my numerator I have 1 minus 2. And on the bottom I have the sign of 0. Now I'm going to go ahead and write 0 from the left, and you'll see why in just a minute. But in the top I have a negative 1. Great, no problem. I am going to come down here and draw a sine curve. There's my pi, there's my negative pi, but I'm really interested in what's happening at 0. I'm asking myself, what is the sign of 0 if I'm coming in from the left? So here's, am I approaching? Yeah, I'm approaching 0. That's been the problem since day 1. We're dividing by 0. But be careful, because we're dividing by not 0 if we're coming in from the left, but all of these y values are all negative. So I'm going to write down a 0, but it's negative. And you know what? I'm even going to write something like this. Negative 1 divided by negative 0.00. I'm just going to, you know, something really small. So the top was not a problem. The bottom is something really, 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 really close to 0, but negative. And this kind of takes us back to this idea. A negative divided by a negative is a positive. 1 divided by something really, 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 really tiny is something really, 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 really big. In fact, we used that phrase last year. Last year we said 1 divided by tiny equals big. Okay. I'm kind of pausing to kind of let that kind of sink in. Right? So again, we could not technically plug in the 0, but because they were asking from the left, we said, well, okay, it's something really close to 0, but it's going to be negative, and that got us to where we were here. Let's talk about from the right-hand side. From the right, same function. So it's not going to be a problem on the top. I'm still going to have 1 minus 2. But now when I plug in the 0, but I'm coming in from the right, let's talk about those numbers. I'm going to change colors here. Coming in from the right on a sine curve, I'm getting close to 0, but those numbers are all really, 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 really tiny, but they're all positive. A negative divided by a positive is a negative, and 1 divided by something really tiny is something really big, like infinity. So this is something we worked with last year. We're getting a little more technical than last year. We're not necessarily going to use words like big and tiny. I'm going to say in the world of limits, and you're going to hate me because you're going to say we've been told our entire life you can't divide by 0. Well, you're absolutely right, and I'm not changing that. But what we can do is say, well, what are we getting close to? So 1 divided by something tiny is something really big. 1 divided by 0 is going to be some form of infinity, either positive or negative. We'll have to determine the sign by doing what we did here. Is it a positive small number? Is it a negative small number? Okay. So while we technically can't plug in the 0, we can kind of think about something just to the left or just to the right. Okay? All right, let's do something a little simpler here. So over the last few days, we've been looking at limits to a point, right? As x approaches 3, as x approaches 0, as x approaches pi. However, and we talked about this last year in pre-calc, we can also look at functions as x approaches positive or negative infinity. The notation hasn't changed, but instead of a number here, we're going to have an infinity, right? And the idea is we're going to get farther and farther and farther away from the origin in both directions along the x-axis. What is the y value getting close to? In essence, we've been doing this since Algebra 2. Well, I guess you could even say Algebra 1. A limit to infinity is asking what are the ends of your function doing? What is the end behavior? Okay. All right. So it says evaluate each limit by inspecting the graph. We should be good at that by now. Then state the equation of any horizontal asymptotes. All right, here we go. Here's our first graph. It looks like I'm calling it h of x. What is the limit as x approaches infinity? And infinity is like a million, bajillion, gazillion. I'm making up words. My graph goes out to 15. So we're going to have to kind of make some assumptions. So if I'm trying to get out to infinity, don't start all the way over here. Don't start all the way over here. Let's start, you know, on this side of the graph. So here we go. I'm going to take my pen. I'm going to start walking along this graph. X is getting bigger and bigger and bigger. My y values are maintaining their position at 2. Okay. Next question, what is the limit as x approaches negative infinity? Well, again, here's my x-axis. Start on that left side and start going back to negative infinity. My graph is going to go to negative 15. What are those y values getting close to? They are getting close to 2. My question is, does this graph have any horizontal asymptotes? And I think a lot of us, going back to that first slide when we were reviewing that parent graph of 1 over x, would say, yeah, this graph has 2 asymptotes. Looks like it has a vertical asymptote and a horizontal asymptote, and it absolutely does. Now it says state the equation of, right? A horizontal line is a y equals. Good. Let's take a look at the next graph. A little more going on here. Same 2 questions. What is the limit as x approaches infinity? So again, there's a lot going on in the middle, but a limit to infinity is not asking about the middle, it's asking about the ends. So kind of start on the edge and walk your way out. What y value are we getting really close to, or what y value are we staying really close to? And that y value is 1. Let's go out to the other side. Again, don't get caught up in the middle. If you start over here, you're never going to get to negative infinity. So start on the left and continue walking left. What's staying also close to y equals 1. Does this graph have a horizontal asymptote like this one does up here? I'm going to pause for a moment while you ask yourself that question. Now, a lot of us might look at that and say, no, right? I mean, look, you can't draw, and I'm putting this in there for a reason. But you might think, well, this end is out here and this end's kind of flattened out, but gosh, this crossed and you know, ugh. There's a lot going on in the middle. This graph does indeed have a horizontal asymptote at y equals 1. Why? Because, and when we flip our notes over, we'll see this, because the graph in the ends takes the shape of that horizontal line. That's a definition we talked about last year in pre-calculus. Okay. I want you to notice this. Look at all these things that match. 2, 2, 2, 1, 1, 1. The limit to infinity was 2. The limit to infinity was 1. The horizontal asymptote was 1. That's not a coincidence. Let's flip our notes over. It says we can find horizontal asymptotes by evaluating a function's limit to infinity. Here's a formal definition, and I'll explain with words. If the limit as x approaches positive or negative infinity of a function is a constant, then your function has a horizontal asymptote, and the equation of that asymptote is y equals that constant. I'm going to put that in words, slightly different. If the ends of a graph resemble or take on the shape of a horizontal line, then the function has a horizontal asymptote, which is that line. My handwriting could be better there, and I apologize. If the ends of a graph look like a line, that means your function has an asymptote. I'm going to flip my paper back over. Pause this if you need to finish writing that down. Oh, going back here, let's say that I had, oh, well, look, I'm having a late night snack. Let's say that I had dropped a piece of chocolate, oh, dark chocolate. Let's say that I had dropped a piece of chocolate on my paper, and I said, oh gosh, I don't see the middle of that graph, but what is that graph? If I ignored or couldn't see the middle, and all I could see were the ends, wouldn't you say, oh, Mrs. Patton, that's the graph of y equals 1. That's why we say that graph has a horizontal asymptote, because no matter what's going on in the middle, the ends look like that line. What if my chocolate had been dropped up here? Same thing. The only part of that graph I see is y equals 2. It looks like that chocolate is covering a horizontal line, even though we know it's not. I'm going to eat that chocolate later. That's my treat for the end. All right, I'm going to flip my paper back over. Okay. So let's take a look at our graphing calculators. Again, I'm going to use my Inspire, but we'll talk about using an 84 or I have talked about it, but we'll talk about it in a video that I'll add here. So I'm going to go ahead and start a new document. I'm going to bring my calculator up here. I'm going to cover up that right side. But it says use your graphing calculator to investigate. I'm going to go add a graph page, and I'm going to graph this one right here. Right, we don't graph the limit, we just graph the function. So I have 3x plus 1 on top. I have that absolute value of x. Whoops. And then outside those absolute values is a minus 4. Okay, so we can change the window in a moment, but it says what is the limit as x approaches infinity? They want, and by the way, second question, negative infinity. So we'll do those both together. They want to know what's going on in the ends. I can change the window, I can fumble around with this, I can drop chocolate in the middle of the page, and we can do that. I think there's a faster way. I think we go back to the table like we were doing the other day. So I'm going to hit Control T. There's my table. Now I could sit here and start arrowing down, but think about it. I'm going out to 5, I'm going out to 10, I'm at 20. 20, 30, I'm really far away from infinity. When we talk about infinity, we're talking about 100, 1,000, 1 million. So I am going to change my table. We did this the other day. Menu, number 2, number 5. It doesn't matter where we start like it did the other day, but let me just tell you, if you're trying to walk to Cleveland, you do not take baby steps. If you're trying to get far away, you're going to take giant steps. Oh, I don't know, maybe 1,000. That's a pretty big step. Whereas the other day we were doing 0.001. All right, well look at this now. Look at my change in my table. And now when I start going down, I want to keep going until I don't see much changing. Well, I don't, look at those first 3 digits. 3.000, 3.000, 3.000. I'm pretty pretty comfortable saying, like we're out at what, 62,000 and my y values are all hovering around 3. I'm pretty comfortable saying that the limit as x approaches infinity is 3. I mean, we're at 62,000 and all those y values were pretty darn close to each other. And they're coming down too, right? 0.22, 0.22, 0.21. I want to go do my next question, which is negative infinity. Well, that's easy. Let's just go the other direction now. You might find it quicker to start back at 0, so you don't have to hit that arrow button so many times. Now, I'm not going to stop when I get to 10,000. I'm going to go until I see a pattern that I'm comfortable with. And my 3 digits after the decimal place are all 0, 0, 0. So I'm back at that negative, what, 50,000, and I see negative 3.000 in all of my y values. So I feel pretty good saying that on the left side, we're at negative 3. Now I know this is a different question, but does this graph have any horizontal asymptotes? Or does it have a horizontal asymptote? If you want, you could have done this right off the get-go. You can go back to that graph. I certainly wouldn't go from negative 10 to 10, right? That's not very close to infinity. Maybe I would go something like negative 200 to 200. I didn't click on it very well. Right? And think about if I drop my piece of chocolate in the middle and you couldn't see that, wouldn't you almost think, oh, I see a graph y equals 3, y equals negative 3. You almost see 2 horizontal lines. So yes, this graph has 2 horizontal asymptotes. Y equals plus or minus 3. Because my limit to infinity was a constant, so I have a horizontal asymptote there. Okay. Let's talk about this next one. The limit as x approaches positive or negative infinity. A new page, a graph page, because I have a new function. Make sure your calculator is in radians. So we have the sine of x all over x. And this question is asking for the limit as x approaches positive or negative infinity. Kind of talked about this graph the other day, but we were really focused on what was happening in the center. I'd like to know what's happening at the ends. So I am going to menu, just kidding, escape. I'm going to control T first. Menu 2, 5. Doesn't matter where we start, but if we're trying to get out to infinity, I better take giant steps. If we're trying to go the distance, take big steps. So let's start going. And what you'll notice is some of them are positive, some of them are negative. But what are all those y values really close to? Now be very careful when you look down at the bottom there. That's tricky, isn't it? I think that's going to be in some scientific, yeah, look at that, that's in scientific notation. That's not helping us out here, is it? What are all these y values? They're really close to 0. And by the way, if you kind of hover over with your mouse, you might see it pop up in yellow, a bigger number. Maybe not. Okay, never mind. There it is. Oh, no, went away. Point is, look at all of these y values. Although some are positive and some are negative, they're all still really close to 0. Let's go the other way. So I'm going to go menu 2, 5 again. I'm going to start at 0 again. And now I'm going to go backwards and tell me what you see with all those y values. Even though they're going back and forth between positive and negative, they're all still really, really, really tiny. And we're going to review this graph here, but no matter which side I'm going to, those y values were getting really close. Remember this graph from yesterday? This is the graph that had the hole up at the 0.01, and then we said it oscillates, but as it oscillates, it dampens. And dampens means it's going to get the amplitude gets shorter and shorter and shorter. So that's why it's bouncing back and forth, positive and negative. But the limit is 0 because this graph is approaching 0 in the ends. That graph, if I drop my chocolate on the middle, would start to resemble the line y equals 0. Okay, really good visual aid today. Glad I have that here. Okay, sorry. All right. not with calculator, but I just want to talk about different things you'll see, because that positive negative thing on this one I think would have thrown some folks off because they would have felt like they weren't seeing a pattern. All right, I'm going to add a new page again, and I have another fraction, and I have x cubed plus 2x squared minus 1. On the bottom I've got x plus 4. The question is, what is the limit as x approaches infinity? Right, with my pen, follow it up, but it looks like it's going up, 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 but I'm only at like x equals 4, so I don't actually know what's going on over here. So with that being said, I'm going back to the table. I don't ever really want to trust a graph unless I really change the window. So I'm going to go ahead and hit Control T. And I'm going to menu 2, 5. Doesn't matter where we start, but if we're going to infinity, I better take giant steps. So let's take a look at some of those. Already when x is 1,000, I'm at almost 1,000,000. 2,000, I'm at 4,000,000. I mean, what's happening to those y values? They're getting large, aren't they? Very, 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 very large. So, as x approaches infinity, y approaches infinity. So it is okay that our answer is infinity, and we saw that the other day. Well, we saw that on the front of our notes today. All right, let's finish up. So let's finish up by talking about what we call an end behavior model. This actually, you've not called them end behavior models before, but you know exactly what this is. An end behavior model, I will abbreviate that as an EBM, is the parent function that will tell us graphically what the ends of our function are doing. So, for instance, find the end behavior model for this function right here. I'm not asking you to graph this function by hand, but you could all tell me what shape it has. Based on what we did in pre-calculus, you'd all say, oh, that's a cubic. Oh, I know what a cubic looks like. It looks like this. That's an end behavior model. The end behavior model says we only need the highest powered term to determine what our function will be doing as x approaches positive or negative infinity. So I know that this graph will look like this in the ends. I'm not saying that's what this graph looks like, but it's telling me what the ends are doing. The left side is going down, the right side is going up. So as x approaches infinity, as we look at the right end, that graph is going up forever. As x approaches negative infinity, or as I go to the left end, this graph is going down to negative infinity. So you know that. But there are parent functions. An end behavior model is just going to help us determine what the ends of the function are doing. Well, let's take it a step further, right? We can do it for polynomials. Let's do it for rational functions. It says for each function, find and sketch the end behavior model. I'm looking for a very simple graph. Then use your graph to evaluate each limit. So I've got two separate problems here. Let's take a look at this one. In the top, I have a 4x to the, now I just covered it up, it said 4. On the bottom, I have a negative 2x. The end behavior model says this graph will look just like this graph in the ends. Oh, we know what that graph looks like. It's a horizontal line, isn't it? This is my end behavior model. This is what my graph, this is what this graph is doing in the ends. They both look like the line y equals negative 2. So as x approaches positive infinity, that right end is flattening out at negative 2. As x approaches negative infinity, that end is also flattening out at negative 2. That's it. The end behavior model says, look, I'm dividing this function by this function, but this function is dictated by its highest term, this function is dictated by its highest term. Let's do the last one. So when I look at this one, the end behavior model, In the top, I've got a 3x cubed. In the bottom, I've got an x squared. I picked the highest power on the top and bottom, and now I'm going to reduce that, and I'm left with 3x. Oh, we know what that graph looks like from Algebra 1. It's a line with a slope of 3. Which tells me that if I were to graph this graph and cover up the middle with a piece of chocolate, it would look just like this in the ends. An end behavior model tells us what the ends are doing. So, as x approaches positive infinity, as I go look here, and as x approaches negative infinity, as I go to the left, this graph is going down forever. And we'll continue this discussion a little bit more in our next lesson.